in the last two sections, 4.5 and 4.6, we've seen two different ways of regularizing an operator. One was TSVD, truncated singular value decomposition, and the other one was Tichonov regularization. And now in section 4.7, we're going to compare the two. Okay, let's see what's coming out. If you ask 100 random people on the street what comes to your mind when you hear the word regularization, then 90 of them will say Tichonov. No, actually, if you ask 1,000 people on the street what comes to your mind when you hear the word regularization, then 900 will say what's that, and then you ask the other 100, and out of them 90 will say Tichonov and 10 will say TSVD. Why is Tichonov so much more famous and used than TSVD? Well, one of the main reasons is it doesn't need singular values. So computing the singular value decomposition of your operator is costly, it's numerically expensive, and you don't have to do that for Tichonov. All you need is, well, you need the adjoint operator and you need an inverse and some multiplications. That's not cheap, but it's better than having to compute singular values and vectors. And those 10 people who answered TSVD are probably a bit more on the theoretical side, because if you work theoretically, you can just pretend you have your singular values and then you prove nice theorems. And that's often a bit easier and maybe cleaner for the TSVD. Okay, let's have a comparison of the two. And in order to compare them, you have to get them on equal ground. And that's singular values. So let's start by translating Tichonov regularization into the language of singular values. So suppose you have a singular value decomposition of A, and then let's see what the Tichonov solution operator for A looks like. Actually, we also need a little lambda. Okay, and then let's plug in the Tichonov formula. And now substitute U sigma V star wherever you see A. And then that's what you get. And I think I don't have to say much anymore about the adjoint of a product being the product of the adjoints in reversed order. Because U is unitary, its inverse is U star, so when the two of them meet, they just cancel. And then here with this identity operator, let me just do the opposite trick. Let me write that as V times V star, because that's also the identity, because V is also unitary. Okay, let's write down this new line. Okay, and I think now you can see why we did this trick here. Because we have V and V star also here and here. So that we can factor out V to the left and V star to the right. And then we know that we should write an identity here again in order to avoid a syntax error. Okay, now let's compute the inverse of this product here. So we have 3 factors. And for these you have to reverse the order and put the inverse down to each one of them. Okay, but the inverse of V is just V star, and the inverse of V star is just V. And I guess there is not much we can simplify about that term here. But by associativity we can clearly erase these blue brackets here. And then notice happily that again V star and V meet here and cancel. Okay, and that's already the singular value decomposition of your Tichonov operator. You have a unitary operator to the left, a unitary operator to the right, and a diagonal matrix in the middle, because it's diagonal matrix here, diagonal matrix here, inverse of a diagonal matrix is still a diagonal matrix, and the product of two is also one. If we call the diagonal entries of sigma just S1, S2, and so on, like we always do, then this new matrix here would be diagonal, as we said, and it has the following entries. I mean, here you get Si squared, and then you add lambda squared, and then you take the inverse. Okay, and from here you just get another Si multiplied. Working with diagonal matrices is so easy, almost like just multiplying numbers. Okay, so if these are the singular values of A, then those are the singular values of the Tichonov operator for A. And that's what I meant by saying let's express Tichonov in terms of singular values, because now we can compare it to the TSVD. Well, actually one more little step is required because we've been a little unfair. Let's look at the TSVD again. We defined the TSVD regularizer to a given parameter epsilon of your A to be the operator where you just copy everything except the singular values that are less than epsilon. They are replaced by zeros. And then that's your new and improved A with a smaller condition number, a smaller pseudo-inverse. Let's just abbreviate it by A epsilon. And then instead of solving AX equals or approximately equals B, you plug in your new and improved A. But when we discussed Tichonov regularization, we found this operator that takes your right-hand side B and turns it into your Tichonov solution X, and that's what we called the solution operator for Tichonov regularization. Okay, but now here with TSVD, the situation is still a bit different because our TSVD regularization operator still is applied to X and produces B, so we have to take that the other way around. So your least square solution X here is the more Penrose pseudo-inverse of A epsilon applied to the right hand side B, and now that's your solution operator. That takes your right hand side into your TSVD solution. Okay, and that's just to be fair, we should put the more Penrose inverse here, and therefore also here before we can compare it to this Tichonov operator up here. Okay, but we know how to compute the pseudo-inverse of your operator if you're given its singular value decomposition. You just exchange U and V, and you replace the singular values that are non-zero by their reciprocals, and you leave the zeros as they are. So now these numbers on the diagonal here are the singular values of your TSVD regularizer pseudo-inverse. And now we can start comparing these numbers here. By the way, note that the singular vectors are the same. So you have V coming from the left here and U star coming from the right here and here. So let's start a nice long table here where we compare the singular values of A inverse, well, if it exists, then the solution operator for TSVD with parameter epsilon, and finally the Tichonov solution operator with parameter lambda. Okay, A is just where we put down the notations, and we said that the singular values of A are the numbers that we denote by SI, where I is running from 1 to N or M. then the singular values of A inverse are just 1 over SI, and you can see that this is only possible if none of the little si's is 0 and if m equals n. For TSVD and Tichonov, let's look up quickly what we got here. Well, for the TSVD, we get the reciprocals of the singular values that are greater than or equal to epsilon. And we get 0 if your singular value was less than epsilon. Okay, and for Tichonov, we just have to copy that expression here. And that's your comparison. Okay, I can understand this is not great if you don't see graphs or something. So let's get the graphs in here. Well, 1 over SI as a function of SI has a graph like this. We know this. This is just 1 over x as a function of x. Then for the TSVD, this changes a little bit. Now you get this graph. So for values below epsilon, your function value is not 1 over s, it is just 0. So in a sense, you're cutting off this bit of the graph, which is close to the singularity and which is producing the huge numbers, and you keep the rest. So this value here must be 1 over epsilon then. And that's how you can see how you have limited the norm of your solution operator from possibly huge down to at most 1 over epsilon. Okay, now Tichonov, the graph of this function as a function of SI looks like this. So it's of course a bit different to the blue curve. I mean, if you're going in this direction, if you're making your singular values large, then both of them look very much like the black curve, which is the idea. You want to mimic the behavior of the inverse, but you don't like the behavior of the inverse close to 0 because there it's going crazy. And TSVD is treating that craziness a little bit different to Tichonov. It's a simple analysis 1 exercise to show that the local maximum of this function is at point lambda, and the function value there is 1 over 2 lambda. Okay, and now for better comparison, let's look at the blue and the red graph in the same diagram. Okay, and now you can see that for better comparison, I took epsilon equal to lambda, so the point where the blue function is jumping is equal to the point where the red function is maximal. And you can see that the function values at these points are just, blue is just twice red. Blue is 1 over epsilon and red is half of that. Okay, we already said that towards plus infinity, where singular values of the solution operators are small, the blue and the red function both mimic the black function. So let's try to write blue as black times something, and then the same with red. Actually, let's squeeze this a little bit here. Okay, and maybe we have to move this a little bit. Excellent. And now let's try to write this TSVD singular value function here, which is the blue graph, as the black graph times something, or as 1 over SI times something. And here's the something. So it's just a characteristic function that deletes everything below epsilon and keeps the rest alive. So the function value where it is not 0 is 1. Okay, so this blue curve here is this black function times this cutoff function. And that's why we find TSVD is so simple or clean, because it's just a simple cutoff applied to the function that you naturally have. Okay, now obviously for a comparison we need to see what goes here. And this is the graph of the missing factor. Well, we can almost copy the analytic description from here. We just have to add a little square up here so that one of these two SI factors here can cancel with that one to give you this result. Okay, so let's squeeze everything a little more so we can show a comparison of these two graphs in the same diagram. Excellent. And now let's bring this comparison in. And now we can nicely see that they both tend to 1 as s goes to infinity, which of course means that for large singular values you get the same behavior as in the black curve. Okay, but they have different strategies to deal with the singularity close to 0. Black one just simply cuts off, and the red one does a somewhat soft cutoff. Okay, we said it before, the jump of the blue function happens at point epsilon, which in our comparison here is equal to lambda. And at this point the blue function jumps from 0 to 1, and the red function is just a half. You can easily see that by plugging lambda into this formula for SI. Okay, and that's what I wanted to show you in this section where we compare TSVD and Tichonov.